Welcome back to another lecture in our series of lectures on introductory materials informatics. So far we have discussed something about how do we work with images, specifically in terms of how we can capture the salient features of an image by using probability distribution and representing it using microstructure function and 2-point statistics. And then we also discussed a little bit about how we can do reconstructions of the microstructure once we have some starting image to work with. The reason we are focusing so much on microstructure is because this is the one thing which is going to connect the processing of materials and the properties of materials. In other words, how you process the material is going to affect the microstructure, and the microstructure of the material is going to affect the properties of the material. Now, it's not just the microstructure only. If you, for instance, are doing some kind of a non-equilibrium processing, it's not just that the microstructural features are different, sometimes even the phases can be different, and that can also lead to different types of properties. So, not just the microstructure, but even the crystal structure that should be captured as a function of the processing and how that affects the properties of the material. And it is this part that we are going to focus upon today. So you will see a figure like this quite commonly in the world of material science, where people talk about something called a materials tetrahedron. So in case of the materials tetrahedron, we think that the 4 vertices represents the performance of the material, the structure of the material, the processing conditions, and the properties. So if you look at the interlinks, you will see that how you do the processing is going to affect the structure, and then what the structure is going to affect the properties. And if you know the type of properties you want, you are basically going to control how you process the material. Now, if you know this structure property processing triangle, then this is also going to influence how the material is going to perform in a real world condition. So this is how the processing, structure, and properties of the material is related to performance. Now, one important thing comes at the center of this materials tetrahedron, and this is basically the type of characterization you are doing. Now, the type of characterization you do is going to determine which length scale you are actually looking at, whether you are using something like an optical microscope, whether you are using X-ray diffractometer in order to get the crystal structure, or you are using a scanning electron microscope or a transmission electron microscope. That is going to affect the type of length scale that you are able to visualize, the type of structural level at which you are going to describe the material. So this type of processing structure property linkage is going to be extremely important for us from a materials engineering standpoint, especially as we try and design materials with carefully chosen and carefully targeted properties. Now, if you look at the different types of processing methods, which is essentially the first part of your PSP paradigm or the processing structure property paradigm, you can see that we can broadly classify the processing methods in 3 types. So you could have solid state processing. So solid state processing, typically you think in terms of powder metallurgy. So what you are basically doing is you might be starting with some form of solid particles when it comes to the solid state processing or powder metallurgy. And then basically what you do is you will end up consolidating these particles, and this process of consolidation is going to happen by using techniques like pressing or some form of molding. Once you have a initial green body, meaning something which has not yet been densified, just the powder particles which have been pressed together, this can be sintered, which basically means that you will heat it at high temperature until the atom starts diffusing and start coming close to each other, resulting in a dense body. Or you could be doing some method like a extrusion process, where you basically feed the billet through a die and you extrude it to get into a dense, narrower component. Or you could even be working in a heat treatment lab, and you might be doing heat treatment where all you are doing is not changing the shape of the material per se. All you are doing is taking the material, heating it to different temperatures, holding it for long enough time, and what that can accomplish is it would result in some form of homogenization, it could result in some form of phase transformation. And so if you actually take it to high temperature, induce the phase transformation, there is a chance that if you quench it or cool it very rapidly, you will be able to trap the high temperature phase. There is that chance. So depending on how you process, you are going to start affecting the structure of the material. In addition to solid state processing, you could also have processing from the liquid. This is in fact a very common way of making materials. Here, essentially what you are doing is you have some starting materials, and all of the starting material you are going to heat, and you are essentially going to melt by heating. So then what you have is liquid. And after that, what you basically do is you control how this liquid is going to freeze. So as you control the freezing of the liquid, you will end up with your casting or your solidified product. And by controlling how the liquid is being cooled, how the liquid is being frozen, you can actually generate different types of microstructure. So this is another processing condition where your choice of the process parameter is going to affect the final structure of the material. And then finally you have got vapor phase processing. So things like inert gas condensation or chemical vapor transport, where essentially what you do is you will have species in a vapor phase or a gas phase, and then after that they might be reacting or they might be condensing in order to give you your final product. So for our purpose, we'll probably be focusing more on the first two parts, which is processing from liquids or casting solidification type of processing, or processing in the solid state, so which could be sintering, injection molding, extrusion, heat treatment, dry pressing, that type of conditions. But the main point that I want to get across is as you change your processing method, you are actually starting to change the structure of the material, whether it is at the level of crystal structure in some cases, if it's highly non-equilibrium, or if it is at the level of the microstructure itself. So the reason I wanted to simply give you a feel for different processing methods, and it's really a very cursory survey of the processing methods, because there are so many different types of processing methods. Once you have a feel for the processing methods, the next thing you have to think of is how are you actually going to featureize the process parameter. Because if you want to make a machine learning model, you better find a way in which you can incorporate the features. Right? So how do you featureize processing parameters? You can think of featureization by doing some sort of categorical encoding, which we also call one-hot encoding. So for example, I'll take the heat treatment of steels. Suppose you have heated the steel to a austenizing temperature, and after that you are quenching. So what is your quenching media? Is your quenching media oil? Is your quenching media water? Is your quenching media something like a brine solution? So there is no way in which you can actually take convert this new oil or water or brine into numerical values. So therefore what you have to do is you have to employ one-hot encoding, and you have to assign a numeric value for each of this media. So this is how you can use categorical encoding in order to featureize your process parameters. So in this particular case, the process parameter we talked about was the media in which you are doing the quenching. Then you have got direct numerical encoding. So for instance, if you are doing a solid state processing by let's say heat treatment, then the temperature at which you are doing the heat treatment, that is a number, that is something which can be used as a feature. In addition to your categorical or numerical encoding, you can also opt for using derived features or this physics-based features. So for instance, if you want to know which type of crystal structure might be forming, especially if you start moving into non-equilibrium processing conditions, you might actually want to know what possible structures are there, and then start calculating the formation enthalpies of those structures, maybe start calculating the entropy, configuration and entropy of those structures, and so on and so forth. So here the value of formation enthalpy, maybe the value of the size of the grains that you are forming, all of those things play into the physics of phase selection. So this would be a way in which you can actually do some sort of physics informed encoding by using features which are calculated using physical principles. Then of course you could have some statistical distribution of processing history. So for instance, you might be looking at a galvanizing line, and then in the galvanizing line, before you actually do this dipping, you pass the sheet through different furnaces, and you will be having not one single temperature, but you might actually have a distribution of temperature when you are looking at an industrial scenario. So statistically, what temperature you are targeting for this process, as well as what is the standard deviation when you measure the temperature over long periods of time, those type of descriptions can also come in. And then if you are doing some sort of imaging, so let's say if you use a thermal camera during your processing, then how your material appearance starts changing as captured by the thermal camera can also be used as a process parameter. Usually we will be more concerned with the first three types of featureization for the different process parameters. So again, if I take the example of heat treatment of steels and then I start looking at the process parameters, I can look at categorical features which would be in terms of the quenching media as we described. The direct numerical features can be in terms of the temperature of the at which we are doing the heat treatment. So let's call this the austenizing temperature, something of this sort. Then you can have the physics informed features. So physics informed features, now you can basically try and leverage the information that you get from phase diagrams or something that you get from a TTT diagram. So all of those things you can include, and then after that you have to develop this process structure linkage. So when we talk about the process structure linkage, one should also be very clear about what structure we are talking about. I'll just go over it very briefly because we have been talking about representing structures in the last few lectures. So it can be in terms of the electronic structures. So electronic structure features could be something like the ELF or the electron localization function. These are things that again can be calculated using density functional theory. You could be having the density of states, that could be one type of structural description, or you could be having what we call the spaghetti plots, which are essentially the representation of the band structure of the material. You could also have structure represented in terms of the crystal structure, and as we have discussed quite extensively, the crystal structures are where you can think of them as graphs, where your atoms are acting as nodes, and then the bonds between the atoms, we think of them as edges. Then of course, when you talk of structure, it could be microstructure, and you can have features such as, let's say, the grain size can be a feature. You could have some sort of anisotropy that you would have to find a way of capturing when you are describing the microstructure and so on. And as you go to the really large scales, there things like the component geometry starts to matter. So for the purpose of this course, we are not really going to talk too much about the component geometry. We will focus mainly on the crystal structure and the microstructure. So once you have an idea of how you will featureize the process parameter, and once you have an idea of how you want to represent the structure and therefore know how to featureize the structure, we can start developing the processing structure linkages. So when I'm developing the processing structure linkages, I have to start with the original data set. And so when I start with my original data set, I basically have my processing features in the data set. I will have the structural data, and the structural data can typically be in form of images like the microstructure, or maybe some snapshots of what the crystal structure looks like. And then I will have to do proper featureization, but then before I use the microstructural features, let's say, I have to do suitable data dimensionality reduction. So techniques like using the principal component analysis and all, that becomes important over here. So the important thing is, I am trying to stress to you that we are not really directly correlating the processing features with the structural data. There is the intermediate step that we have discussed, and this step is about doing the data dimensionality reduction in order to get a smaller set of more relevant features. And it is with this reduced data dimension and with reduced number of features that we will go ahead and train the model in order to establish the link between the processing condition and the structure. And so once your database is ready, you have to use a suitable machine learning model. So things like artificial neural networks, things like random forests or transformers, it depends on what type of problem you are looking at and what model works the best for your specific situation. So you have to use this model and you have to train the model. So if you train the model, the next thing you want to ask yourself is, what is this model being trained on and what output are we expecting from our model? Okay, that is something which is going to be important. So once we know that, then we can create the model, we can train the model, and then after that you want to validate the model. Now ideally you don't want to validate the model on the same training data set. So it would be a good practice that if you have a new data set for validation containing data which does not appear in the training data set. Okay, so for model validation, essentially you have to make the prediction, you have to compare your predictions with the actual values, and so you will need some sort of a input in order to make the prediction, and the input would come in terms of what your processing features are, and after that, once you know your processing features, you should be able to generate the microstructure functions, the probability distributions, or at least basically the set of reduced features which appears over here in your training data set. After that, what you want to do is, once you have the sample features, you want to now start expanding and you want to start reconstructing the entire structure using the probability distribution. And this is where the microstructure reconstruction that we were talking about in the previous lecture comes in handy. Okay, so if you are able to reconstruct the microstructure, then now you are in a position where you have already developed this processing structure linkages. Now, we were talking about processing structure and properties. So we already saw how we want to establish the processing structure linkage. Now we have to move toward establishing the structure property linkage. And so for that, let us look a little bit into material properties. So when we look at material properties, you can have many different classes of properties. So I'm just listing a few common ones over here. So for instance, when you look at mechanical properties, you might be interested in predicting something like the yield strength, or you might be interested in predicting the hardness values, or you might be interested in predicting the Young's modulus, whatever it is. Now, you will find that some of these properties will be very composition dependent, whereas there are quite a few properties which depend heavily on the microstructure. The hardness or yield strength, for example, is quite sensitive to the microstructure. Then you can have thermal properties. So things like the coefficient of thermal expansion, thermal conduction, that type of thing is another type of properties that are of interest in a variety of materials. So if you are working with high temperature materials or whether you are working with thermal insulators, having an idea of the thermal properties is always going to be good, and having the ability to predict the thermal properties will also be quite useful. Then you have got electronic properties. So when we talk about electronic properties, we are basically looking at things like, for example, the band gap. So if you are going to work in the semiconductor domain, electronic properties are going to become quite important for us. Sticking with the electronic properties, tuning the band gap can also help change the optical properties of the material. So optical properties is again something that people are interested in, especially nowadays with a lot of people getting interested in plasmonics. Optical properties of materials are also quite important. Magnets is another thing which is very commonly used in a lot of technologies, and so magnetic properties of materials, what would be the BH product or what would be the saturation magnetization, those type of things are again things that people will want to be predicting. If you work with high temperature materials, you will be having degradation of the material as a result of its contact with oxygen. So things like oxidation or corrosion, that becomes very important in a variety of applications, let's say like gas turbines, aircraft engines, and so on. So the bottom line is, when you are looking at these properties, in addition to having the numeric values, it is really important that you have a good understanding of the physics of the problem. Because once you understand the physics of the problem, you will be able to figure out what type of featureization is needed, whether you at all have to look into the microstructure or you can live with the atomic structure or maybe even the composition. So that is a decision that you have to make, and that's why knowing the physics of the problem, knowing the basic material science that you are addressing is going to be useful for you as you start developing this PSP paradigm. So how do you go ahead and featureize the properties? Once again, you can have different types of descriptors, categorical descriptors where you do a one-hot encoding. So here maybe whether something is metallic or ceramic or polymeric, that matters. Especially if you have a situation where you are doing some amount of classification and you want to convert that into a numeric value, this type of categorical descriptions will be quite useful. Then once again, just as in case of the process parameters, you can have direct numerical encoding. So here, for instance, if you are looking at mechanical properties and you do a measurement of the yield strength, and that comes out as 358 MPa type of value. So now what you basically do is you have got a numerical value with which you can train your model. So you can have a numerical feature. Many times the properties of materials are not isotropic. So anytime you have got an isotropic, there the tensorial properties or the vectorized features, that becomes important. You might actually have to look at the directionality of the property that you are looking at. Statistical distribution, again, you might be having a microstructure which is not perfectly homogeneous, and then different regions of the microstructure may have different concentration of different phases. So on an average, how the values are changing in a given region, how the values are changing. So you would be working with statistical distributions. You might be representing the variation of properties across the material in a statistical manner, and that might be another way in which you can train the models. Many times, people also work with dimensionless numbers. So especially people who are working in the domain of fluid mechanics or materials processing where good amount of fluid mechanics is involved, they often use dimensionless numbers in their work. And so this is another way in which you can featureize your problem. Then you have got this option of looking at temporal curves. So basically any property which is going to be time dependent. So for instance, when you are looking at a corrosion problem, you might be having the increase in the amount of corrosion product that is forming as a function of time, and the same thing can also happen as a function of temperature. So you could have properties which are time dependent properties, which you could have properties which are temperature dependent properties or pressure dependent properties. So you would have to then featureize the properties accordingly, and by and large you'll be looking at this 5 things for most of the time, that you either do some sort of a categorical description, or you come up with a vectorized feature which captures the anisotropy, or you look into the direct numerical encoding. So that's how you start featureizing them. So once you know how you want to featureize the properties, it is now time to move on to developing the structure property linkages. And when we try and develop the structure property linkage, once again we need a basic data set with which we will be working with, and then this data set is something which is going to contain the structural data. As we have said before, the structural data can typically be in form of images. What would be really useful is if you can also encode the composition, or if you can superimpose the local composition variations on the microstructure. So once you have your structural data, the next thing is again to featureize the structure, do some data dimensionality reduction, and then you want to correlate this reduced features with the properties. So this is how you will start and build a link which starts from the structure of the material to the properties of the material. And once you have this data set, you will again use different types of machine learning model, and then you will be training your model. Now, the next question you want to ask is, what is this model being trained on? It's being trained on the data set that you have curated, and then what output is expected. So whatever property you want to predict, that is the output expectation that we have got. So as with earlier, once you train your model, you will need to validate your model, and again you want to work with a fresh data set when you are doing the validation of the model. For the validation part, what you have to understand is we are going to start with the image or start with the structure. We will feed the structure to our model, and then that structure needs to get featureized properly. So you have to extract the microstructure functions and the probability distribution functions, and from there you will have to predict the property. So even when you are training and you are looking at your training data set, you will notice that the properties are essentially being linked with the featureization of the microstructure after you have done the data dimensionality reduction, and that is exactly the same thing we are doing. You take the microstructure input, you do some dimensionality reduction, you extract the features, and then using those features and your trained model, you will go ahead and predict the property. Now, once you have established the processing structure and the structure property linkage, it is now time to go ahead and integrate and come up with your integrated processing structure property linkage. And this is where the concept of transfer learning becomes useful. So essentially, if you look at our workflow, if you look at the computational pipeline that we have to build in order to establish this processing structure property linkage, you will see that our first step starts with the processing parameter, where you want to convert the processing parameters into proper feature. After that, you want to predict the structure, which is going to be in terms of probability distribution functions, starting from the processing parameter. And then from that structure, you want to get into a situation where you can predict the physical properties. Now, as you are predicting the structure from the processing parameter, you can even reconstruct it and get your microstructure images as an output as well. So if you look at this computational pipeline, you will see that on the left side, if you look at these three boxes are essentially what we were talking about when we were discussing the processing structure property. In other words, you can think that these three boxes together, they represent what we can call machine learning model number 1. Then when you look at the three boxes from the right hand side, you will understand that these are the exact three things that we were looking at when we were trying to establish the structure property linkages as well. And so this now becomes our machine learning model 2. So what we are essentially doing is we are learning from one machine learning model, using that as an input for the second machine learning model, and then getting our final output. So you are transferring the knowledge from one ML model, and then you are transferring it to your second ML model, and you are using. Now, when you actually develop the processing structure property linkages, it is always a good practice if you can simultaneously include the composition as well, because in addition to the structure, the composition of the material also matters in terms of the properties that the material has. So you will understand that the composition which can be expressed or which can be featureized using this composition based feature vectors or other calculated features like, let's say, the thermodynamic features, for example. So once you have this composition featureized properly, you can actually combine it with the processing parameters in order to get a better prediction of the structure and hence a better prediction of the properties. And in many cases, you will see that the only property you are trying to predict are intrinsic properties, in which case you can actually bypass this PSP linkage and then go straight away from the composition to the final property prediction. So this is basically what we mean in terms of this processing structure property linkages. Now, when you look at this processing structure property linkages, there is no need that you have to go only in one direction. This computational workflow can also be reversed, and therefore you can think in terms of creating these PSP linkages as forward linkages, or you can think of creating these PSP linkages as inverse linkages. So what we are doing now is we are broadly classifying the problems into two categories, and then we will be approaching these problems accordingly. So in the first case, what we are essentially doing, we are predicting the properties once we know the processing conditions. So from processing conditions, we are going to the structure and then using the structure to predict the property. This is a fairly straightforward method. That is what we discussed. But many times when you are doing materials engineering, you actually know what properties you want, and therefore you now have to solve the inverse problem. And so what I basically mean by that is, you know your target properties, use these target properties in order to determine which type of structure you want, and then use this structure to determine which type of processing you want. So if you can address the problem in this manner, this is actually quite attractive, but then you do have some limitations in setting up the inverse problems. And one of the most important limitation comes if your data is multi-valued, if your data is not single valued. So what that basically means is when you are starting from the opposite direction, you are starting with a property, but then the property might be a multi-valued function. In other words, it is not necessary that only one specific structure will give this value. You might actually have an array of different structures from where you will be able to get this type of properties. Second is, when you are looking at engineering problems, you are usually not going to look at only one single target property, but you might be actually looking at an assortment of different types of target properties. And it may so happen that one of those properties in this assortment that you are looking at would be related with one type of structure, whereas the other properties might require a different type of structure. So in such a case, if you are looking at it as an inverse problem, this is something which is going to become very hard to solve. But I just wanted to put it out there so that you understand that when you set up this type of machine learning problems, it's not necessary that you always start from the processing, go to the structure and then to the property. You can actually think in terms of creating inverse problems and then solving the inverse problems. And that might actually be more useful in number of situations, but just be advised that this is not always possible. So with that, we are now going to stop here for today's discussions. And thank you very much for joining with us and listening to this lecture. And as we move forward in our next lecture, we shall start discussing about how we look into explaining and interpreting machine learning models. Thank you.